Okay, in today's class we'll be discussing something very important. This concept has a lot of applications with regards to the upcoming topics, so let us just start. The concept today is mixing involving noise. Let me just write it down. Mixing involving noise. Alright, now this particular concept can be divided into two parts. Let us first of all start with the first part, and this is mixing noise with sinusoid. So what are we going to do exactly? Now we are going to start with the same old equation which we know regarding noise. So let's begin. Consider the noise random process n of t, which is equal to limit delta f tends to 0 summation k running from 1 to infinity ak cos 2 pi k delta ft plus bk sine 2 pi k delta ft. Now let me just call this as equation 1 over here. Now we very well know that the spectral component of n of t at frequency k delta f is nk of t, which is equal to ak cos 2 pi k delta ft plus bk sine 2 pi k delta ft. Now let this be equation 2. Alright, now moving further ahead, we have that power spectral density of nk of t is gn k delta f, which is equal to ak square plus bk square whole divided by 2. Let me just scroll down. It is ak plus bk divided by 2. Now to be more exact, it is going to be ak square bar plus bk square bar whole divided by 2. And now let this be equation 3. Now coming to PSD of the basic noise itself is gn of f. Now this is simply equal to limit delta f tends to 0 summation k running from 1 to infinity Gn k delta f. That is what we have. Now let this be equation 4. I hope you understood the relationship between the power spectral density of the overall noise over here to the power spectral density of its spectral component. So that is the significance of equation 4. Now consider mixing, which is nothing but multiplying nk of t with a deterministic sinusoid cos 2 pi f naught t, where f naught is arbitrary frequency. So we have nk of t cos 2 pi f naught t. So this is mixing of the spectral component of noise with a deterministic sinusoid of an arbitrary frequency. Now this product or mixing is going to result in two random processes, nk minus L of t plus nk play plus L of t. Now let this be equation 5. Okay, so let us have a look what these two random processes are, where nk minus L of t is simply equal to ak by 2 cos 2 pi k delta f minus f naught of t plus bk sine 2 pi k delta f plus f naught of t. Now let me just call this as equation 6. Now moving on, n k plus L of t is equal to ak by 2 cos 2 pi k delta f plus f naught of t plus bk sine 2 pi k delta f plus f naught of t, and let this be equation 7. Okay, we obtain equation 6 and 7 by substituting equation 2 in equation 5. That is as simple as that. And from equation 5, 6 and 7, one thing should be obvious for you. By mixing noise spectral component with a sinusoid has resulted in two new spectral components of noise which are the shifted versions of the original noise spectral component. So this is a very important conclusion that we can make from equations 5, 6 and 7. So let me just also write this. The two new spectral components are the first one is Nk minus L of t. Now it should be obvious to you, is a spectral component of N of t at frequency K delta F minus F naught. Let me just correct this. I think there's a mistake over here. This is supposed to be, just give me a second, there is a mistake. This is supposed to be K minus F naught and K plus F naught. K plus F naught. Okay. So let me just K minus F naught, and on a similar note K plus F naught of t is a spectral component of F naught of N of t at frequency K delta F plus F naught. So this is what we have by mixing a noise spectral component with noise. The result is the sum of two new spectral components where both the spectral components are shifted versions of the original spectral component we have. Now let us talk about the power spectral density of Nk minus F naught of t, and it is nothing but Gn K delta F minus F naught. Now let us just go back to equations 6 and also 7. Before that, let me just remind you something. Now have a look over here, have a look at equation 2. Now equation 2, we very well know that that is a spectral component of noise, and equation 2's power spectral density, which is given in equation 3, is nothing but the sum of the squares of the random variables that are present in that equation whole divided by 2, and of course we have taken the statistical average. Okay, so the sum of their squares whole divided by 2 is the power spectral density associated with the spectral component at k delta f. Now if you have a look at equation 7 over here, the random variables associated with the power spectral component k minus delta f is ak by 2, and let me just correct it, this is bk by 2 and this is also bk by 2. So the random variables are ak by 2 and bk by 2. So the power spectral density associated with the spectral component at frequency k delta f minus f naught is equal to ak by 2 whole square bar plus bk by 2 whole square bar whole divided by 2. This is what we have. Now this is nothing but gn of k delta f whole divided by 4. This is what we have over here, and let me just call it as equation 8. I hope you understood. On a similar note, I can also say that PSD of the spectral component located at k plus, beg your pardon, k delta f plus f naught is gn k delta f plus f naught, which is equal to again gn k delta f whole divided by 4. Now this is equation 9. Now let me just write down equations 8 and 9 should be understood in the correct context. Now what is the correct context over here is, have a look. Equation 8 says that the power spectral density of the spectral component at k delta f minus f naught is equal to 1/4 of the power spectral density corresponding to the spectral component at k delta f. Now this relationship, whatever you are seeing, this relationship holds good in terms of magnitude only, and the same is the case over here also. This gn power spectral density with respect to the spectral component at k delta f plus f naught equal to 1/4 of power spectral density with respect to spectral component at k delta f. This relationship also holds good only in terms of magnitude. Alright, gn k delta f minus f naught and gn k delta f plus f naught can be obtained by first dividing gn of k delta f by 4. Okay, one second, I think there's a grammatical mistake. By first dividing gn k delta f by 4 and shifting the result to the left. I'm sorry, okay, let me get it right. To the right by f naught, comma, to the left by f naught. Or in other words, if you want this, you can get it by first taking GNK delta f, dividing it by 4, and then shifting the result to the right by f naught. This is how you obtain the power spectral density corresponding to the spectral component at k delta f minus f naught. And if you are looking for this, the power spectral density with respect to the spectral component associated with frequency k delta f plus f naught, the process is the same. Divide Gn of k delta f by 4 and shift that particular result to the left by f naught. This is what is supposed to be done to get the spectral densities corresponding to the new spectral components that have resulted because of the matching process. So this is what we have. Now let's go to the next step. Consider nk plus f naught of t plus nk minus f naught of t. Let's check whether superposition of power applies to this sum. So we very well know that for superposition to apply, superposition in power to be applicable, time average of the statistical average of nk plus f naught of t into nk minus f naught of t dt should be equal to 0. This is supposed to happen for this sum of random processes to have superposition of power to be applicable, and we derived this relationship in the previous lectures. So let me just call this as equation 10. Now if the expectation or the statistical average of this product is constant with respect to time, then the superposition of power will be applicable if this product or the statistical average of this product is equal to 0. That's it. So this is a special case now. This is a special case of equation 10. So let me just call it as equation 11. Now let us first of all calculate the product of these new random processes. Just a second. F naught of t times k plus f naught of t. So this is nothing but ak by 2 cos 2 pi k delta f minus f naught of t plus bk by 2 sine 2 pi k delta f minus f naught of t. This is what we have into ak by 2 cos 2 pi k delta f plus f naught into t plus bk by 2 sine 2 pi k delta f plus f naught into t. So this is what we have. Now let me just call this equation as equation 12. Now we know that the random quantities in equation 12 are only AK and BK. In addition, we know AK bar is equal to BK bar is equal to 0, comma. We also know that AK BK whole bar is equal to 0 and AK square bar is equal to BK square bar. We know these, so let these three results put together be called as equation 13. Now taking statistical average of equation 12 and making use of equation 13, we get, let us just have a look. So it's going to be expectation of nk minus f naught times t to nk plus f naught of t, which is going to be equal to simply ak square bar by 4 into cos 2 pi k delta f minus f naught into t and cos 2 pi k delta f plus f naught into t and bk square bar by 4 sine 2 pi k delta f minus f naught into t sine 2 pi k delta f plus f naught into t. So this is what we have, and this is further going to reduce to something like this: cos of 2 pi k delta f t minus 2 pi f naught t minus 2 pi k delta f t minus 2 pi f naught t. This is what it is going to reduce to, and this is going to be simply equal to cos 2 pi minus 2 f naught times t, which is equal to a k square bar cos 2 pi, let me just 2 f naught t. So this is what we get. Now let me just call this as equation 14. Now one thing is clear from equation 14, it's obvious expectation of nk minus f naught of t into nk plus f naught of t is dependent on time. So this is what we have. Since it is dependent on time, we need to apply the time average, as we have already seen with respect to equation 10. So from equation, okay, 1 second. So applying time average to equation 14, we get limit t tends to infinity 1 by t integral over t expectation of nk minus f naught into t nk plus, beg your pardon, nk plus f naught of t f naught of t dt will be equal to, if I bring a k square bar outside, now I think there is a mistake over here. This is not a k square bar simply, this is a k square bar by 4, k square bar by 4. So this is going to be k square bar by 4, and this is also going to be a k square bar by 4. Limit t tends to infinity 1 by t integral over t, and we have cos 2 pi into twice of f naught of t dt. So this is what we have. Now assuming t to be an integral multiple of f naught, it can be said that the above equation becomes limit t tends to infinity 1 by t integral over t expectation of nk minus f naught of t nk plus f naught of t dt is equal to ak square bar by 4 into 0, which is equal to 0. So we can finally conclude one thing from thus from equation 10 it can be said that superposition of power applies to nk minus f naught of t plus nk plus f naught of t, or let me just put it down in equations. Power of nk minus f naught of t plus nk plus f naught of t is equal to power of nk minus f naught of t plus power of nk plus f naught of t. So this is the meaning of application of superposition, and of course you know that already. Now this can be further extended to power spectral densities. Thus PSD of n of k minus f naught of t plus n k plus f naught of t is equal to PSD of n k minus f naught of t plus PSD of n of k plus f naught of t. But there's one thing which we need to remember. So let me just call this one as equation 15. Now from equation 5 we have nk minus f naught of t plus nk plus f naught of t is equal to nk of t cos 2 by f naught of t. So from equation 5 and 15 it can be said that power spectral density of nk of t cos 2 pi f naught t is equal to power spectral density of nk minus f naught of t plus psd of nk plus f naught of t. So this is what we finally conclude. Now if we substitute equations 8 and 9, then we'll have, let me just write down over here, substituting equations 8 and 9 in equation. So let me just call this as equation 16. In equation 16 we have PSD of nk of t times cos 2 pi f naught t is equal to gn k delta f minus f naught plus gn k delta f plus f naught. This is what we have. Now let me just call this equation 17. Now applying limit delta f tending to 0 to equation 17, we have PSD of n of t cos 2 pi f naught of t is equal to limit delta f tending to 0 PSD of nk of t cos 2 pi f naught t is further equal to limit delta f tending to 0 PSD of, I have nk minus f naught of t plus limit delta f tending to 0 PSD of nk plus f naught of t. Now this is simply nothing but 1/4 of gn f minus f naught plus 1/4 of gn f plus f naught. This is what we have, or let me just write it, PSD of a noise spectral component mixed with noise, a noise spectral component mixed with a sinusoid, which is nk of t cos 2 pi f naught t, where f naught is arbitrary and cos 2 pi f naught t is deterministic, is simply equal to 1/4 of gn f minus f naught plus gn f plus f naught. So this is the conclusion we arrive at, and let me just call this as equation 18. Now let us just mention this equation 18 in words. Now let me just have a look. From equation 18, it can be summarized that if the power spectral density Gn of f of noise random process n of t is given, then the power spectral density of a noise mix with a sinusoid can be obtained from the following 4 steps. So let us just write down what the steps are. The first step is divide Gn of f by 4. The second step is shift Gn of f. Okay, 1 second, let me just put it in much better words. Shift the result in step 1 by f naught to right, and shift the result of step 1 by f naught to left, add the results in steps 3 and 4 to obtain the PSD of nk of t cos 2 by f naught t. So this is how you can obtain the power spectral density of nk of t times cos 2 pi f naught t, which is nothing but mixing noise with a sinusoid. Let me just correct this, there is a mistake. It is n of t times cos 2 pi f naught t, not nk. It is n of t times cos 2 pi f naught t. So this is how you compute the power spectral density associated with noise that has been mixed with a deterministic sinusoid of arbitrary frequency. Now this completes the first part of mixing with noise. Now let us go to the next. Okay, 1 second. This partially completes the first part of mixing involving noise. So let us just continue where we have now we have from equation 1, let me just rewrite equation 1. So this is what we have. We have n of t equal to limit delta f tends to 0 summation k running from 1 to infinity ak cos 2 pi k delta ft plus bk sine 2 pi k delta ft. So this is what we have. Now let us extract two spectral components of n of t, one with frequency k delta f and other with frequency L delta f. Now k and L are arbitrary numbers, so you can consider them to be any values, not an issue. Now, so we can simply write it like this: nk of t. Let me just write down. So the two extracted spectral components are nk of t equal to ak cos 2 pi k delta ft plus bk sine 2 pi k delta ft. And on a similar note, we have, just a second, n L of t equal to al cos 2 pi L delta ft plus bl sine 2 pi L delta ft. So this is what we have. Now let me just call down these equations as equation 19 and equation 20. So this is what we have. Now consider a deterministic sinusoid with frequency f naught, where f naught is equal to k plus L into delta f divided by 2. Or I can simply write it down that f naught is located midway to k delta f and L delta f. This is what we have. So now let's consider n k of t cos 2 pi f naught t. Now we very well know what the result is going to be from equation 5. So let me just write it down over here. It's going to be n k minus f naught of t plus n k plus f naught of t. Now let me just call this as equation 21, and on a similar note I can also say that n L of t cos 2 pi f naught of t is equal to n L minus f naught of t plus n L plus f naught of t. Let me call this one as equation 22. Now let's consider one second. Okay, one second. Okay, let's consider n k minus f naught of t and n L minus f naught of t. Now I can simply write that we have f naught minus k delta f equal to f naught. Okay, one second. It is going to be half k delta f plus half L delta f minus k delta f, which is equal to half of L minus k delta f. Let me just call this as equation 23, and we also have L minus k delta f is equal to, one second, there's a mistake. L delta f minus f naught is equal to L delta f minus half k delta f minus half L delta f. So this is equal to half L minus k delta f. So let this be equation 24. Now we come to a very important conclusions from equation 23 and 24 that f minus k delta f and L delta f minus f naught result in the same frequency. So let me just write down, considering equations 23 and 24, it can be said that f naught minus k delta f is equal to L delta f minus f naught, which is finally half of L minus k into delta f. Let P delta f be equal to half of L minus k delta f. So this is what we get. Now let me just write down. Now I can simply say that n, we have k minus f naught of t equal to ak by 2 cos 2 pi p delta f t minus bk by 2 sine 2 pi p delta ft. So this is what we get. Now let me just call this equation as 25. Now, and we can also simply write it down like this: k plus f naught of t equal to, beg your pardon, this is just a second, this is going to be L plus f naught, 1 second, this is L minus f naught. So L minus f naught of t is going to be AL by 2 cos 2 pi p delta ft plus BL by 2 sine 2 pi p delta ft. Now let me call this as equation 26. Now let np1 of t be equal to nk minus f naught of t, and np2 of t be equal to n L minus f naught of t. Let me just write this down properly. L minus f naught. Now let me just go further ahead. Fine. Now what are we going to do is, let us consider the superposition of np1 of t and np2 of t. That is np1 of t plus np2 of t, and let's investigate for the application of superposition of powers of np1 of t plus np2 of t. Or in other words, we are just going to find out whether power of np1 of t plus np2 of t is equal to power of np1 of t plus np2 of t or not. We are just going to check whether this particular equation holds good or not. So that is what we are going to see. Now for that, we very well know if the time average of the statistical average of the product of these two is equal to 0, then superposition of power applies to np1 of t plus np2 of t. So let us see what we have now. Now let's have a look. This is nothing but np1 of t and this is nothing but np2 of t. Now the random variables are ak, bk, al and bl in this case, and the angle is the same in both. So let me also mention, or let me just remind, okay, now we have AK bar equal to BK bar is equal to AL bar is equal to BL bar, and it is equal to 0, and AK comma BK comma AL comma BL are independent to each other. So expectation of np1 of t into np2 of t is simply equal to 0. It should be very clear to you why it is 0. Now if you simply multiply both of them, we are going to have AKAL again cos square, and over here we have minus BKBL by 4 sine square, and then the cos products AKBL cos sine and minus BKAL cos sine. So we'll be having 4 terms, and the random quantity in each of the 4 terms has an average mean of 0. So that's the reason why all the 4 terms will average out to 0. So the final answer is the sum of 4 zeros, which is equal to further 0. Thus, so np1 of t plus np2 of t contain or possess, let me just put it in better terminology, contain okay, same mistake again. Possess, let me just write down, possess superposition of powers, superposition of power, not powers, possess superposition of power, or in other words, we very well know power of np1 of t plus np2 of t is equal to power of np1 of t plus power of np2 of t. So this has been proved. Now let us calculate something else as well. Consider expectation of np1 of t plus np2 of t, and it should be obvious that this expectation is equal to 0. And we already know that expectation of np1 of t is equal to expectation of np2 of t is equal to 0. So variance of np1 of t is simply equal to expectation of np1 of t square comma variance of np2 of t is equal to expectation of np2 square of t. Now in this case, from looking at the top 3 equations, it can be said that power of np1 of t is simply equal to variance of np1 of t, which is expectation of np1 square of t. On a similar note, I can also write that power of np2 of t is equal to variance of np2 of t, which is equal to expectation of np2 square of t. This is possible because np1 of t and np2 of t are stationary. And since superposition of power applies to np1 of t plus np2 of t, it can be said power of np1 of t plus np2 of t is equal to expectation of np1 of t plus np2 of t whole square, which is further equal to variance of np1 of t plus np2 of t. This is possible because of np1 of t plus np2 of t results in a stationary random process and np1 of t plus np2 of t's statistical average is equal to 0. So I can finally conclude that variance of np1 of t plus np2 of t is equal to power of np1 of t plus np2 of t, which is further equal to variance of np1 of t plus variance of np2 of t, which are nothing but power of np1 of t plus power of np2 of t. So this is what we have. Now, since superposition of power applies, we can also say that PSD of np1 of t plus np2 of t is equal to PSD of np1 of t plus PSD of np2 of t, and this should be same as the result we obtained just a while back, which is 1/4 Gn k delta f minus f naught plus gn L delta f minus f naught. So this is what we have. So the power spectral density of the resultant random processes by multiplying or mixing the given spectral component of noise with a deterministic cosine side can be easily found out from this particular relationship.